Okay, in this video, I am going to use optimization techniques to minimize the variance of a portfolio. So the scenario we have is we have two stocks. We have expected returns for those stocks for the next year. We have the standard deviation of the returns for those stocks for the next year. We have the correlation between those returns for the next year, and we're trying to construct the portfolio with the minimum variance. Okay, so we have the expected return for the first stock is 6%. The expected return for the second stock is 8%. The standard deviation of the returns for the first stock is 20%. The standard deviation for the returns of the second stock is 15%. And the correlation between those returns is negative 20%. So I'm going to try to find the portfolio with minimum variance. And I'm going to solve this in two different ways. The first, where it is unconstrained, we are going to allow the investor to short either of the stocks. And the second, where it is constrained, we are not going to allow the investor to short either stock. So let me go to my scratchpad here, and I'm going to introduce a variable W1, which is the weight of the first stock. Irrespective of our constraint, the weight of the second stock is 1 minus W1. So that's the weight of the second stock. And the constraint, if we so choose to have it, is 0 is less than or equal to W1 is less than or equal to 1. And that will make sure that neither stock has a negative weight, or meaning that one of the stocks we would short. Okay, so we want to minimize the variance. So if I look at the variance of a portfolio of two stocks, that's going to be W1 squared times the variance of the first stock plus W2 squared times the variance of the second stock plus 2W1 W2 times the covariance. Okay, so what do we know? We need to calculate some variances here. So the variance of the first stock is equal to 0.2 squared equals 0.04. The variance of the second stock is 0.15 squared, which would be 0.0225. The covariance is equal to the correlation, negative 0.2, times the standard deviation of the first, so 0.2, times the standard deviation of the second, 0.15, and I'll pull out my calculator just to be careful. 0.2 times 0.2 times 0.15 is, again, we have a negative sign, so that's equal to negative 0.006. All right, and we substitute into our variance equation. So variance equals W1 squared times 0.04 plus 1 minus W1 squared, that's the second weight, times 0.0225 plus 2W1 times 1 minus W1 times the covariance, which is negative 0.006. All right, so let's simplify this a little bit. Let's see, let's expand out these products. So we get 0.04 W1 squared plus 1 minus 2W1 plus W1 squared times 0.0225 minus 0.012 times W1 minus W1 squared. And let's gather up our terms. So that's 0.04 plus 0.0225 minus minus, so plus 0.012. That's all our W1 squared terms. And then our W1 terms are going to be minus 2 times 0.0225, so that would be 0.045 plus 0.012 W1. We add all of this up. 0.04 plus 0.0225 is 0.0625 plus 0.012. Let's just make sure and not mess up. 0.04 plus 0.0225 plus 0.012 is 0.0745. 0.0745 W1 squared plus that'd be 0.057 W1. Okay, so that's our variance equation. In order to minimize variance, we are going to, there should be a minus sign. Let me erase that. We've lost the minus sign right here. That should be minus. Okay, so in order to minimize variance, we need to find critical numbers. So we take the derivative of variance, and that would be 2 times 0.0745 times W1 minus 0.057. We check, make sure that's defined everywhere, which it is, and we multiply that out. 2 times 0.0745 is 0.149. So 0.149 W1 minus 0.057 is our derivative. To find the critical numbers, we set the first derivative to 0. So 0 equals 0.149 W1 minus 0.057. And so W1 equals 0.057 divided by 0.149. 0.057 divided by 0.149, 38.3%. So weight 1 is equal to 0.383. That's our critical number. And we want to check whether this is a maximum or a minimum. So we will just check, we'll take the second derivative. So the second derivative of variance is 0.149. So this means the function is concave up, which means we have a local min, which is good, but it is our only, as it is the only critical number. It must be an absolute minimum. So W1 equals 0.383, which would of course mean W2 equals 0.617 is our absolute minimum. Now in this particular instance, thinking about our constraint, 0 is between W1 and W2. This is within that constraint. So this satisfies the constraint we have. It satisfies the domain we are allowed for W1. So it turns out, because of the extreme value theorem, which said that if there's exactly one critical point in the domain, then that critical point must be the absolute min or the absolute max on that domain. We know this must be the absolute minimum both globally without any constraints, but also if we constrain the weights to be between 0 and 1.